Alright, this is the Day 21 lecture video. Today we're talking about sampling distributions, but more importantly, today is the day that we're finally going to start talking about statistical inference. First day of class, I shared a quote that statistics was the art of distilling meaning from data. It's the procedure of taking information and using it to say something about the real world. And we haven't really done that yet. Today, and for the rest of the semester, we're going to finally be working on these questions. If we have some data set of incomplete information, how can we say something about where this data set comes from? How can we make some statement about the real world? I want to again make the distinction between information about the population and information about a sample. So just to recap some notation, the information that we're talking about is often things like the average or the standard deviation of a distribution, or maybe we're talking about the proportion or the percentage of the population that falls into one or another categorical variable. When we're instead talking about the sample, we have the same ideas. We would still talk about the average of the sample or the standard deviation of the sample, but we use different notation. So this is going to start being more important when we start flipping back and forth between these two ideas. So same concepts, different notation. We've been talking about probability. Questions like, if we assume that I make 30% of my free throw shots and I attempt 10 shots, how many shots do I expect to get? What can we say about what the sample or what the results are going to look like? So I would argue that probability is going in this direction. If we are assuming that we understand what's happening, if we understand the rules of the game, if we understand what my probability of making a free throw shot is, what can we then say about what happens if I do the thing, so in this case, shoot some free throws, for a number of instances? One question that might be asked is, where did this 30% probability number come from in the first place? Well, it's probably from, past performance. Maybe the last 100 free throws, 30 of them were made, or something along those lines. Well, how do we know that 30% is actually the right number? So probability is saying we're assuming that we're assuming that this 30% number is right, and we're asking what we might see if we were to test this. Inference, and statistics in general, is asking the opposite question. If I were to go out to test my free throw shooting percentage by shooting 10 shots, and I see that I make 3 of them, what does that tell us about my actual value? So if I were to test it, if I were to look at a sample, what information does this tell us about the actual real life value? So in this free throw shooting example, if I make 3 of 10, yeah, my shooting percentage is probably about 30%. But I wouldn't, say like, oh yeah, this is definitely what my number is. Maybe it's somewhere like 20 or 40. And so it's probably 30%, give or take a certain amount. And that idea that, well, we have a good guess as to what it is, but there's a certain amount of leeway, is a very common thing when talking about statistical inference. Moving forward, we'll be talking more about how much exactly we can say about the population if we happen to know a certain something from the sample. Probability assumes that we understand the rules of the game and asks what we might see if we were to test this, whereas inference looks at what we get when we test something and asks, all right, what can we say about the rules of the game? I want to point out that I'm using this term population in a more general way. So yes, we could be talking about, let's say, the proportion of people in the US who plan to vote Democrat in the coming election. But we could also use it to mean the quote-unquote true value of something. Let's say my true free throw shooting percentage, or the probability of making a single shot. Okay, we're not actually done with probability. In order to be able to answer questions about inference, we're often going to have to ask this hypothetical question of, well, if the population happens to have a certain proportion or a certain mean, in that scenario, what types of samples do we expect to get? So we are going to be using probability to answer these hypothetical questions. Today we're mostly working with categorical variables. So if we have a collection of individuals, we might ask how many of them have a certain property, what proportion of them fall in a certain group. For example, if we are asking what proportion of people in the US are planning to vote Democrat rather than Republican or Libertarian or whatnot, the party they intend to vote for is the categorical variable, and the thing that we're measuring is what proportion of a group falls under a certain category. Free throw shooting can also be a categorical variable. Each individual shot can be one or two categories, either a make or a miss. And again, we can talk about the proportion of the total sample or the total number of shots that falls into one category or the other. All right, let's walk through an example of what I mean by a lot of this. So let's assume that vanilla is the favorite ice cream flavor for 30% of people in the country. All right, again, this is a probability question. We somehow know that this overall number, which by the way is p, in this case the proportion is 0.3, we somehow know that this population value is 30. So assuming that we know that, then what do we expect a sample to look like? So this is a question that we could have done last week. The expected value, or the average number of people, is going to be the number of people in the sample times p, which is 100 times 0.3, or 30 people. All right. We're going to ask a slightly different question, but really the same thing. The expected value of the sample proportion, as in what is the percentage of the sample that we expect to have vanilla as their favorite flavor, well, that is just going to be p, right? So we're not scaling this up by the number of people in the sample, we are just leaving it as is. So this would be 0.3. So 30% of our sample would be, we would, yeah. All right, so this equation may seem a little bit silly, but let's talk about what exactly it's saying. It's saying that if the overall number, if the population proportion is a certain value, then if we were to take a sample, on average, the proportion of that sample, so the percentage of this 100 people who have vanilla as their favorite, that proportion on average is going to be the same thing. That said, just due to the random nature of taking a sample, we would expect some variation, which is where the standard deviation comes in. So the standard deviation for the distribution, for the total count of how many people there are, is the square root of n times p times q. Well, if we want to turn this into the standard deviation for the percentage, so rather than talking about the standard deviation for the number of people who like vanilla, we want to know what's the standard deviation for the percentage or the proportion of people who like vanilla. We can divide by n. So to get from the count over here to the proportion here, we divided this term by n and we got p. Same type of thing is going to happen over here. So our equation for the standard deviation of the sample proportion is the square root of p times q over n. So to get from here to here, we just divided by n. So we're asking 100 people, is your favorite ice cream vanilla? And the expected value of the count of that, of the number of people who say yes, is 30, but due to the randomness, there's some variation, and we would expect the standard deviation for this distribution to be n the square root of n times p times q, which is about 4.5. So 30 people, give or take 4.5, with a standard deviation of 4.5. Working with percentages instead, 30% plus or minus, or with a standard deviation of the square root of p times q over n, instead is going to give us 0.045. In other words, give or take 4.5%. The only difference between talking about the counts versus the proportions is that, well, we're talking about percentages. So our formulas might look a little bit different, but we're still talking about the same idea. If we were to construct the probability distribution for this, we could come up with a histogram that reflects the probability of each of these outcomes. So just like we've seen before, we should get a histogram that looks roughly like a normal distribution. And the distinction I'm making here is that if what we are plotting along the x-axis, rather than the number of people who like vanilla, we plot the proportion of people who like vanilla. The proportion of this 100-person sample that responds that they like vanilla, we are going to be talking about ranging from 0.3, maybe up to 0.35, etc. Just like we did last time, when we have a probability distribution like this, it can be approximated with a normal distribution. So since we have the expected value, or the mean, and the standard deviation, we can instead work with the normal distribution instead of trying to find exact values of several different outcomes. Approximating by a normal distribution is just that, an approximation. And the smaller the sample size, the worse of an approximation it becomes. So we somewhat arbitrarily decide to have some cutoffs where we say, hey, if our sample size is less than a certain value, or if the ridges on our histogram are a little bit too rough, then we're going to not use a normal distribution to model this. Whenever we take a sample, there's randomness involved. There's going to be some variation in what the sample's values look like, and we can usually approximate the distribution of these possible values with a normal model. In order to do this, we want to check to make sure that a few conditions hold. The first couple have to do with how this sample is constructed. So our first assumption is that each element or each individual in the sample is independent. For example, if we're talking about free throw shooting, we want the probability of making a shot to be independent of the probability of making another shot. If we're talking about what proportion of a population has a certain property, we want our representative individuals to be independent of each other. We don't want to, if we're taking a poll, we don't want to go ask one family. We want independence in the different trials. So this is something that we can't ever actually know is true, right? The whole point is that we don't know how these probabilities of making a free throws relate to each other. We don't know for sure that individual people polled are going to be independent. But this is more of a question of, is it reasonable to assume this? And for a lot of situations we've been talking about, maybe this isn't completely accurate, but it's close enough. Our next assumption is related. It's that our sample was formed through randomization. It's that the people that we're polling were randomly selected. The whole point of all of this statistical analysis, the whole point of this, talking about these sample distributions, is that, well, due to the way randomness works, we can say certain things. Well, these need to be random selections. All right, the next two conditions are the two that are more about, is this normal model specifically appropriate to the data that we have? The first one of these is the 10% condition, which assumes that our sample is less than 10% of the total population. If we start talking about samples that are larger than this, the shape of the sample distribution actually ends up getting skewed and a normal model stops becoming appropriate. So we want to make sure that our sample, the size of our sample, is less than 10% of the population. And lastly, this is the make sure our sample size is big enough condition. The success failure condition says that there should be at least a certain number of failures and at least a certain number of successes. And this is where we're putting in a somewhat arbitrary cutoff. So we want it to be the case that the expected number of successes is at least 10, and the expected number of failures is at least 10. And, well, why 10? There's actually a somewhat reasonable explanation, but for the most part, it's an arbitrary cutoff. That said, it's usually a pretty good one. Once we drop below this value, our sample distribution really stops looking like a smooth normal curve and looking more like a choppy sawtooth curve. All right, to recap all of this, the big picture is that we're gearing up for statistical inference. We're getting ready to say, all right, if we see a certain sample, a certain result from a subset of the population, what does that say about the population as a whole? Much of our logic for this is going to hinge on hypotheticals. We'll say things like, well, if our population parameter is blank, then we have a certain likelihood of seeing a certain statistic. That's what we're doing with sampling distributions. In the hypothetical case that a population parameter is a certain value, and we take a certain sample size, then what do we expect to see? Thanks to the nature of randomness, the values that we expect to see is going to be in some range. There's going to be some distribution of values that the sample might look like. More often than not, this is going to be roughly a normal distribution as long as a few assumptions are met.